In the next problem here, the problem states if x of n be a finite length sequence with x of k equals 0, 1 plus j, 1, 1 minus j. Using the properties of DFT, find DFTs of the following sequences. So here the input x of n is not provided, rather its DFT is given, and without actually finding the value of x of n, they say that using properties we have to arrive at the values which is called as x1 of n, x2 of n, x3 of n. Now the problem is not actually solved here, but rather we shall discuss the approach or method to be taken so that we can proceed in solving the problem. The first problem, if you observe, x1 of n is equal to e power of j pi n by 2 x of n. Now here we have the time domain sequence x of n, which is multiplied by an exponent. So we should identify that this property of multiplying by an exponent in the time domain results in a circular frequency shift in the frequency domain. So therefore we have circular frequency shift property, and the problem is to find x1 of k. Therefore please refer to the property, compare it with what data we have, and try to determine by how much you're going to shift it. So it's quite a simple problem. If you can decode the value of the shift, and then x of k is shifted appropriately, and that result becomes x1 of k. The second problem we have x2 of n equals cos pi n by 2 x of n. The simplification can be done first by substituting cos theta as e power of j theta plus e power of minus j theta divided by 2. And once you do that, now we have a similar looking problem, but it will have two terms. The first exponent into x of n, the second exponent into x of n. Now individually you can apply the circular frequency shift property, and you can get the answer, combine the results, that becomes x1 of k. In the third case, x3 of n is equal to x of n minus 1 mod 4. So here the shifting is done in the time domain. Therefore, this property is called as circular time shift property, and we know in the respective frequency domain we have to multiply it by the complex exponent. So appropriate multiplication of x of k with that exponent will provide you with the answer which is called as x3 of k. So I recommend students to please try this out and come up with the solution. The next problem. A designer is having a number of 8-point FFT chips. FFT stands for fast Fourier transform. It's just a faster way of computing the DFT. It's a more efficient way of calculating the DFT. But the problem is to find DFT. So we have 8-point DFT chips or processors. Now they say show explicitly how he should interconnect the 3 chips in order to compute a 24-point DFT. So the n value here in the problem is 24, but we are having FFTs of size 8. How do you combine it? So the data we have is 24 inputs. Now the first task is to subdivide the given input of length 24 into 3 sequences of length 8 each. Now how you can arrange? First element will go to the first group, second element to the second group, third element to the third group, and again you repeat. So x3, x4, x5, x6, x7, x8. Like that you carry on. The last set of elements will be x of 21, x of 22, x of 23. So here we can collect that. Here we get all the terms which are multiples of 3. Here we get a term which is that plus 1, and here it is the same value plus 2. Therefore, now we can build an equation for the DFT as follows. X of k is equal to summation. The points here indicated that we are taking selected points, like the numbering for n goes as 0, 3, 6 till the last point 21. Next set, numbering for n index is 1, 4, 7, last point will be 22. Numbering for n is 2, 5, 8, the last point will be 23. Now let us write it in the form of a proper equation, and that can be written as shown here. Let us select an index which is called as m. The m ranges from 0 to 7 because each set will carry 8 elements. Now the first set, as we observed, is a multiple of 3. So we can call it as 3 times m, where m is the integer from 0 to 7. Substituting will obviously give you the value 0, 3, 6 till 21. Now since we have changed n here in the power of w of n, we have to replace it with 3m. Therefore, we have 3km. For the next set, we know that the displacement or shift is by 1 point. Therefore, it is denoted as 3m plus 1, maintaining the same index, that is m is equal to 0 to 7. And here also we write 3m plus 1. For the third set, we know the displacement from this is 2 points, 0 plus 2, 3 plus 2. So we write it as 3m plus 2, and here also we have 3m plus 2, maintaining the index from m is equal to 0 to 7. Now let us see if there is a scope for simplifying here. Yes, the twiddle factor can be simplified using reduction. So if we divide the base by 3, the power is also divided by 3. Therefore, it becomes wn by 3 to the power of km. Here also wn by 3 to the power of km. wn by 3 to the power of km. But we have to observe that the second and third summation twiddle factor, the powers has 2 terms, hence you can split it. So in the second summation, wn to the power of k is a constant because it's independent of m. You take it outside the summation. Third summation, wn to the power of 2k is a constant. You can take it outside the summation. And finally, the first part, let us denote it as x1 of k. The second part is wn to the power of k, which is x2 of k. We are using x2 of k as a notation for the second summation. And wn to the power of 2k, x3 of k is the notation for the third summation. Now each of these is an n-point DFT. Therefore, if you are capable of calculating the n-point DFT of these respective set of 8 inputs, then you could combine these 3 8 points using the equation shown here and compute the 24-point DFT. Therefore, this equation can be substituted taking the value of k starting from 0 and going all the way to the last term, which is 23. You will get the answer for the 24-point DFT. So how the interconnection is to be done is suggested using the equation shown here. The next problem states, show that the product of two complex numbers a plus jb and c plus jd can be performed with 3 real multiplications and 5 additions. The terms a plus jb is multiplied with c plus jd, and we expand it. We know that we can get a sequence as ac plus jbc, j times ad minus bd. So if we actually count here, we have 1, 2, 3, 4. See, each product here, a and c, they are real values, b and c real values. So we can actually count that we have 4 real multiplications and we have 2 real additions, because we're going to combine these 2 terms, we're going to combine these 2 terms. So this is the combination, and this is how you get the answer in the normal fashion. But the problem says you have to perform the same using 3 real multiplications and 5 additions. So we are willing to reduce the number of multiplications at the cost of increasing addition. Multiplication is more complex, so I think it's a good option. Now how do you simplify it? So the manner of simplification is suggested here. You can see the term AC minus BD. So let us add a value which is equal to AD and subtract the same value. So we add a value AD and we subtract the same value. And for the second term, imaginary part, we are adding a value J times BD and we are subtracting the same term. As a clue, you can observe here we have AD in the imaginary part, the same AD we add and subtract. And here we have BD and the same J times BD is added and subtracted. This can be thought of as a hint for you to remember the method. Next, we have to see the common terms what we have. So here we have the common term which is D, and you get A minus B times D, and here we are taking the common term which is A. So we get A into C minus D. Once again here taking J common, A minus B into D and J into C plus D into B. Now from this what will you observe? From this we should observe that we have three multiplications. Which are the three multiplications? So A minus B into D is 1, C minus D into A is the second, and C plus D into B is the third. See, this is a repeating, it's a common one which we have already calculated. So we have reduced one multiplication. Now let us count how many additions do we have. So in this expression already you can see, so this is the first addition, this is the second addition, right? This is the third, and you the number of additions we will calculate as 1, 2, 3, 4 and 5. Okay, I repeat again, the number of additions is 1, 2, 3, 4 and 5. So this is how you can support your argument as to how many additions you are able to perform. Okay, moving on to the next question. The next question states, let x of n is equal to 1, 2, 3, 4. Its DFT is also provided. Find the DFT of the sequence x1 of n, and this sequence is obtained by inserting 0 after each value. So 1, 0, 2, 0, 3, 0, 4, 0. Now, without actually finding DFT of x1 of n, we have to get the answer of the DFT. Now, we have to observe the two sequences and somehow try to find the relationship between the two and then solve it. So first, let us write from the definition of DFT. We are aware that DFT of what we want, x1 of n, is equal to x1 of k. And in the DFT equation, we are inserting x of n is equal to x1 of n. Now, dividing this particular summation into odd and even parts. So, the odd part can be represented by considering the value of n to be equal to 2n plus 1. The even part can be considered by taking n to be equal to 2n. So 2n multiples of 2 is even and multiples of 2 plus 1 is always odd. Therefore, we get two summations each carrying 4 points. Since the problem states n is equal to 8, substituting the value of capital N is equal to 8, we are aware that in the sequence x1 of n, each odd term is 0. The even terms have numbers 1, 2, 3, 4, but the odd values are 0. So what happens to the second summation? It reduces to 0 because odd samples are zeros. Therefore, the equation which remains is simply summation n is equal to 0 to 3. Now we know x1 of 2n is identical to x of n. And this Twiddle factor W8 can be reduced by dividing the numerator and denominator by 2. Therefore, we end up with W4 to the power of nk. Now this very much resembles the DFT of the 4-point sequence. So x1 of k should be same as x of k. But since we are looking for 8 points and DFT exhibits periodicity, we can conclude that the first 4 points are given by x of k, that is from n is equal to 0 to 3, and the remaining points are also given by x of k. So we'll just take x of k and write it twice. So we'll take the sequence x of k and write it 2 times. That becomes x1 of k. Let's read the next question. Let x of k be a 14-point DFT of length 14, real valued sequence x of n. The input is said to be real valued. The first 8 samples of x of k are given by, so they have given you x of 0, x of 1, x of 2 till x of 7. They ask you to find the remaining samples of x of k. It's 14 point. They have given you only 8. The rest of the values have to be computed. And evaluate the following functions of x of n without computing the IDFT of x of k. So this is a problem which is like what we have discussed, but it is different. You have to observe it carefully. So here we are asked to calculate not capital but small x of 0, x of 7, summation n from 0 to 13 x of n from 0 to 13 e power of j 4 pi by 7 n x of n, and lastly n is equal to 0 to 13 x of n magnitude square. So to get the first part, the hint is that it's a real valued sequence. So we have to exploit what is called as the symmetry property of real value sequence. So in the solution, we write for a real valued sequence x of n, symmetry property is given as x of k is equal to x conjugate of n minus k. It is same as x conjugate of minus k mod n, but we'll prefer this form. Now let's start substituting now. To compute the answer for k equals 8, let's insert the value k is equal to 8. So the equation becomes x conjugate of 14 minus 8, it is x conjugate of 6. Now we know what is x of 6 from what is given, just take its complex conjugate. So this is x of 8. Similarly, put the value k is equal to 9, solve it, it becomes x conjugate of 5, answer is 6 minus j3. Next, x of 10 is x conjugate of 4, is minus 2 minus j2. X of 11 is x conjugate of 3, it's 1 plus j5. X of 12 is x conjugate of 2, is 3 minus j4. X of 13 is minus 1 minus j3. Moving on to the next part. Now the question asks you to find what is x of 0, small x of 0. The small x is obtained by using IDFT equation. So we write from the definition of IDFT, we are aware that the equation is something like this. Now in this equation, we have to insert the value of capital N is equal to 14. Therefore, the equation becomes 1 by 14 summation k is equal to 0 to 13 x of k e power of j pi by 7 kn. Now to put the value of n is equal to 0, the exponent term, it vanishes. It's equal to 1. Therefore, the answer is the sum of all the elements of x of k divided by 14. So we perform the addition of all the values that is given and calculated, and the sum comes to be 32. And divide the value by 14, we get the answer is 2.2857. The second part of the problem, we are asked to compute what is the answer for x of 7. Similar approach we follow. We take the IDFT equation once again, and in this IDFT equation, we substitute capital N is equal to 14 and small n is equal to 7. And the resultant equation after simplification becomes 1 by 14 times k is equal to 0 to 13 x of k into minus 1 to the power of k. This we are aware because the exponent e power of j2 pi by 14 into 7k simplifies and becomes e power of j pi whole power of k, and e power of j pi is minus 1. So exploiting this concept, we understand that alternating values will have plus and minus, and we perform the addition of all this. The sum is equal to minus 12 divided by 14, answer is minus 0.8571. So students, you are expected to do the substitution and simplification, which is not shown here. Coming to the third part. So in the third part, they are asking you to solve a particular sum. The summation is n from 0 to 13 x of n. Now here we make use of the DFT equation, because DFT equation is the one which gives you a summation with x of n, not the IDFT. Therefore, in the DFT equation, we are letting the value of n to be equal to 14, because that's what is the problem about. So after substituting and after doing simple some modifications, we get the equation which looks like this. Now, in order to eliminate that exponent, we have to make the k value equals to 0. So when you put k 0, this term becomes 1. So this is what we get. And this summation is equal to x of 0. We know the value of x of 0, it is equal to 12. The fourth term is summation n from 0 to 13 e power of j 4 pi by 7 n x of n. Now to solve this, we can compute the DFT of e power of j 4 pi by 7 n x of n. This is the same as e power of j 2 pi by 14 into 4n into x of n. See, why this particular term DFT we are looking at? The answer is very simple. You can see in the summation we have x of n, and this is typical only for the DFT equation. But we don't have simply x of n, we have this term along with it. So we take both terms and we compute its DFT. Okay, so let's work our way. Now, the DFT of this, if you can recollect, since we are multiplying x of n by an exponent, so it results in a frequency shift. So it is circular frequency shift property. So by how much are we shifting? We are shifting it by a quantity which is equal to 4. See, everything else is in place. You know the n value here is 14. So structurally it is in the form of e power of j 2 pi by 14 into 4n x of n. Its DFT is capital X of k minus 4 mod 14. Okay. Now we know that the DFT equation is given by this, x of k is given by this, and therefore if we want the DFT of x of k minus 4 mod 14, then in place of x of n we have to take the quantity x of n into that exponent. So we insert that value in the DFT equation. So after inserting the value in the DFT equation, this is what we get. Now in the above equation, let us put the value of k equals to 0. Once again, this task is performed to eliminate this particular exponent. So we put k is equal to 0. When you put k is equal to 0, the LHS becomes x of minus 4 mod 14. In the RHS, after eliminating the last exponent, what remains is the remaining terms. And this is what we have been asked to solve. So to get the final answer, we just have to reduce this x of minus 4 by applying mod 14. When you add a value 14, we know it becomes x of 10. Therefore, this summation should be equal to x of 10. So substituting that value, we get the answer as minus 2 minus j2. In the last part of this particular problem, we can apply Parseval's theorem, because Parseval's theorem will give you that some summation with a magnitude or mod of x of n square. Therefore, this is the result we have from Parseval's theorem. Here we insert the value n is equal to 14. Therefore, the equation now becomes limit 0 to 13, 1 by 14 summation with limit 0 to 3, 13 for even k also. And since we are interested in finding what is the value in the LHS, in the RHS we shall do the substitution. So expanding the summation and substituting the different values after computing the magnitude square and adding and dividing by 14, your final answer is 35.5714.
Thank you all.